Okay, so what do we got here? We've got a situation where a stone is launched at an angle that they give us an angle, so 65.6 degrees relative to the horizontal, with a speed of 38.1 meters per second from the top of an 81.5 meter vertical cliff. So if I were to draw this picture, it looks a little bit complicated maybe at first, but really it's not that big a deal, and furthermore, I don't necessarily even need to have the whole picture. I mean, I think it's not bad to do, but there's my cliff, right? And then the projectile is just launched at some angle relative to the edge of the cliff, right? Yes. Okay, but remember how we deal with projectile motion, right? We're going to break this into a horizontal part and a vertical part and just treat them independently, right? So what I really need to do then is what? Okay, I need to break up that initial velocity into a horizontal and a vertical component, don't I? Right? And so my initial velocity, let's plug in these numbers. The initial velocity is 38.1. And the angle is relative to the horizontal is 65.6 degrees, right? Okay, so I've got to take that vector and I need to break that velocity vector up into two components. I need to break it up into what we might call my initial velocity sub x and my initial velocity sub y. So the x and y components of the initial velocity, right? Okay, so what's going to be the equation then, that's, or the expression that's going to give me back the x component of that vector? What do you think? So if I want to come up with v naught sub x, what is that? So, okay, 38.1, we got to take the original one and multiply it by cosine. Good, because it's an adjacent thing, isn't it, right? So 38.1 cosine of my angle, 65.6 degrees. Good. And then v naught sub y would be my hypotenuse, right? The whole vector times sine in this case. Okay, because it's an opposite issue, right? And those are just numbers. Those are just calculator numbers. But those are useful. So that's going to allow me to break this up into horizontal and vertical parts. So let's take the horizontal part in that column and the vertical part in that column. So v naught sub x was, what did we say it was? 38.1 cosine 65.6. Okay, and that's just a long way of writing out a number. Right? That's going to be a calculator number. In the y component, v naught sub y, 38.1 sine 65.6 degrees. So once again, just a big ugly number. Okay. What else do we know? Horizontally. Not much really at this point, do we? Right? Don't really know much. That's all we know, is that it's launched from the cliff with that horizontal component to its velocity. Vertically, we know more stuff. There's more going on vertically. What's something else? Sam, tell me something else we know vertically with this problem.
The distance.
Okay, so we know the displacement, don't we? We know that when this problem is over, that's going to be when the stone has covered a vertical displacement of what? And negative, right? Because it's going to start, the stone's going to end up starting here. It's going to launch up in the air and come back down. But vertically speaking, it's going to have just gone up a little bit, but it's going to end up down there. So it's going to have started up here and ended up down there. So either we've got to say the initial position is positive 38.1 and the final position is 0, or more easily, let's just call it a displacement. Either way is fine. So we know that delta y is equal to negative 38.1 standard units, right? Everybody agree? Okay, what else? We know some other stuff vertically. We don't know that, but we could calculate it.
Shouldn't delta y be 81.5?
Yeah.
Oh, oops, I put the wrong thing up there, didn't I? Yeah, you're right. I looked at the wrong number. Sorry about that. So it's 81.5. Right. Sorry. Because that's the distance it falls. Okay, there's something else we know though. Vertically speaking, what else do we know? We don't know final velocity yet. We don't know time yet. We know displacement. What about acceleration? Oh, negative 9.8, right? Okay, so acceleration. So a sub y is just negative g, or negative 9.80, right? And then, let's see, what do we probably need? The stone lands how far from the base of the cliff? Well, in order to get that information, this is how fast it's traveling horizontally. What else do we probably need to know? Time. We need the time, don't we? If we had the time, then we could just use that first equation, right? The horizontal displacement is just going to be its constant, and that's our initial velocity. But remember, what do we know about the horizontal component of velocity for projectile motion? What do you know?
It's equal to the vertical.
No. Now think about when we break this up into, if we look at the flight of an object, right? Something gets launched and it's going really fast and it slows down and then it comes back down. But seen from above, what do you know? It's constant, right? The horizontal component of the velocity is constant, and that's easy to remember because how many forces are acting horizontally? None, right? So there are no forces acting horizontally, so should it accelerate horizontally? No. It's going to just have a constant velocity the whole time. Now, vertically, it's accelerated, right? Vertically, if we watch from the side, it just looks like somebody's throwing a ball up in the air and catching it, right? Okay. So we need time, though, don't we? In order to answer this first part, we need to know what time is. And that's the one parameter that links these two parts of the motion. They're completely independent, but it's still the same object, right? And so it's in the air for the same time, whether it's moving horizontally or vertically. Agreed? Okay, so we could solve for t. That's one thing it might be nice to know. In fact, that's really what we need right here for part 2, isn't it? So which equation are we going to use to solve for t then? Yeah, 3, isn't it? Right? It'd be equation 3. We know displacement, we know initial velocity, we know acceleration, we got to solve for t, right? So we're going to set up equation 3 to solve for t. And what's that give us? It gives us, we'll just write it up here first, delta d equals v naught t plus 1/2 AT squared.
Is ready.
Uh-oh. Okay, so then delta d for us, that's delta y, right? So we get negative 81.5 equals v naught t. So what's v naught? V naught's right here. So that's 38.1 sine 65.6 t plus 1/2 AT squared. Well, 1/2 times A is negative 9.8. We could just write that as minus 4.90 t squared, right? And that's just a calculator problem, isn't it? Right? We can solve that any way we want to. What do you suggest? Let's talk about this for a second. How could we solve that equation? Yeah, I could push everything to one side and use the quadratic formula. That'd be fine. I could also just graph both sides of this if I want to, right? And like graph that and graph that and see where they cross, something like that. Are you guys familiar with that little trick? If I ever want to use a graphing calculator to solve something like this, I could just let y1 equal this side and y2 equal that side, and then see when they cross. Or the other thing I could even do is I could just put this into standard form and graph the zeros. Okay, that works also. So what if I push all this stuff over to this side and I get the equation positive 4.9 t squared minus 38.1 sine 65.6 degrees t minus 81.5 equals 0. So let's just graph that and see what the solutions are. Okay, I'm going to graph it. I'm going to be kind of tricky here. I'm going to show you a new tool if you haven't used this. The calculator works great. Here's another one. Have you used Desmos? Desmos is awesome. So there's my equation, right? I can just go up in Desmos and just type that in. So I'll type in 4.9. I'm going to use x instead of t because Desmos is expecting x's and y's. So 4.9. I wonder if I can use t's. Won't do it. Okay. 4.9 x squared minus 38.1 times sine of 65.6, and I want to make sure I'm in degrees. So I think I can even, how many of you guys have used Desmos? Do you know how to make sure I'm in degrees?
Usually just does.
It's just in degrees. Okay, I think it, graph setting, let's just look here. Degrees. See, look, I want to put it in degrees. So I just went up to the little graph settings thing, and I'm going to put it in degrees. And then I think I just go back. There it is. Doesn't change things a ton, but there it is. Oops. Now what do I do? How come I did that? Oh, right there. There we go. Perfect. Okay. And then minus 81.5 gives me that. And there's my function. Okay, so all I've got to do now is just find the zeros of this thing. So I'm just going to go, there they are right there. One of them is at 4.87, one of them is at negative 4.87. So which one do you suppose I want? The positive one, yeah. So 4.87 is my answer for t then, rounded to two places conveniently.
Could we have just used equation 2
What do you mean?
for the kinematics equations?
The only problem with equation 2 is we don't know what the final velocity is. See what I'm saying? No, because that's going to be vertically, the final velocity is going to be how fast it's going when it hits the ground. Right? You could have used, alternatively, I guess you could have used equation 4 to solve for v, but really it's probably easier just to use 3. Okay? So, all right, so now let's see. So what did we say it was again? 4.87? So if we go back to our, whoops.
Is it 4.7, how far it is from basically?
That's how long, no, that's t. We were solving for t. That doesn't quite seem right to me, though.
I got something within a few points of the second. That's my answer.
You got what?
I got something that seems to be very true with that.
You did get that?
It's effectively, I'm using my numbers, but it's
Mhm.
like within 0.1 of the difference.
See, when I use my numbers, I get 2 points.
I got 4.79.
See, those shouldn't be symmetrical, I don't think. That doesn't seem right to me.
Mine are not symmetrical.
Oh, I didn't put an X there. No wonder.
Oh.
There. Now it's not symmetrical. That's better. Remember, I was supposed to have a T there? You remember that?
Does it matter if we move everything onto the 81.5 side, or if we just move 81.5 onto the side?
It doesn't make any difference. Ideally, you'd like to have that be a positive coefficient, but it doesn't matter. So now, let's just zoom in a little bit so we can see this a little better. So now, yeah, this is better. So now when I look for my zeros, I get 8.941 and then negative 1.86. I want the positive one, right? So mine's going to be 8.94. Agreed? Okay, and then it wants to know, the other part is, so what was it again, 8.94? The other one it wants to know is how far does it land from the base of the cliff? Well, then I would just have to go back to, yeah, over to the X column and say, well, now that I know what T is, I'm just going to use the first equation here, right? We're just going to get delta X displacement is just going to equal V sub X times T, right? Well, V sub X is just that, and T is whatever we had from 8 point, was it 491 or something like that? 941, something like that. And so then that's going to allow me to calculate delta X. I could have just used my graphing calculator. I just wanted to see a different tool here, right? It would have done the same thing on the graphing calculator, right? So what do we get when we do that calculation then? If we do, was it 8.94491? What was it? 941 times this, 38.1 times cosine 65.6, and that gives you my answer. Just make sure I'm in degrees. I am. So there's my other answer. So for part one, it should be 100. What should that be? 100 and 141. Yeah. Right. Oh man. So 141. Okay, makes sense? See how that worked? Once again, there's a lot of stuff, a lot of moving parts there, but really not that big a deal. We just had to break that initial velocity up into components. So we broke it up into a vertical accelerated motion and a horizontal constant motion. And then we just have two separate columns where essentially we just do kinematics, right? Okay, let's maybe look at one more, and then you're off on your own. Okay, this is a good one. So what about this? A steel ball rolls with constant velocity across a flat tabletop 0.961 meters above the flat level ground. It rolls off the edge and hits the floor 0.527 meters from the edge of the table. The ball rolled across the table with a speed of what? Okay. I think that's kind of a clever question myself.
Good job, you.
Yeah, thank you. Tell me how good I am. Okay, so let's think about this in terms of horizontal and vertical motion then. So we just got this ball rolling at a constant speed horizontally across a table. So right as it leaves the edge of the table, what's its vertical velocity? Vertical velocity. No, that's the acceleration, it's negative 9.8, right? Right as it leaves the table, is it moving vertically? So what's its vertical velocity? 0. So the initial vertical component of velocity is 0, right? Right? What now? Well, how come? You're verbally frowning at that.
Okay, so it's rolling across the table.
Mm-hmm.
That means it has to be going this way.
Mm-hmm.
So why wouldn't it be still going that way?
It is. Vertically, it's got-
Vertically.
Yeah. So, in the y direction and the x direction, so vertically speaking, v naught sub y is 0, right? V naught sub x is what we're really trying to find, isn't it? Agreed? Okay, what else do we know vertically? What's the acceleration? Nathan, what's the acceleration vertically? Negative 9.8, good. What's going to be the displacement vertically? When does this, so we really start the camera when the ball leaves the table, right? When's the movie over? It hits the ground. How far did it travel vertically? Negative, right? So our displacement vertically, call it delta y, is negative 0.961 meters, right? Agree? Okay, really all we need to know is time, once again, isn't it? If we knew the time, that would be useful over here. What do we know in terms of the x's? We're trying to find the initial velocity, but what do we know? Delta x. What's delta x?
For you, it's like 527.
Yeah, positive 0.527. It's going to fall off the table and it's going to move sideways that far before it hits the ground. So, right? If we just had t, that first equation would allow us to know what the initial velocity was, wouldn't it? Right? Because horizontally, we know that equation 1 becomes delta x equals v sub x t, right? And this is really, our constant horizontal velocity is the same as our initial horizontal velocity, right? So if we just had t, we'd be in business. We can solve t over in the vertical column, though. What's the equation that would be useful to us there? Equation, no. Which one's it going to be? So we know initial velocity, we know acceleration, and we know displacement. So it's 3 again. Yeah, it's 3. But this time it's going to be easier because,
Initial velocity is 0.
yeah, the initial velocity is 0, so that term drops away, right? So if we use, we're looking for, if we use equation number 3, we get delta y equals v naught sub y t plus 1/2 a sub y t squared. Well, that one's just 0, right? So now when we plug in numbers, we get negative 0.961 equals negative 4.9, 1/2 times negative 9.8 t squared. So what do I do to solve for t?
Divide by -4.9.
Yeah, divide by negative 4.9 and then square root, right? So we get t squared equals 0.961 over 4.9, negative divided by negative is positive, and t equals plus or minus the square root of all that. Well, we'll take the plus one. And that's just going to give us back some decimal answer, right? That gives us back square root of 0.961 divided by 4.9 is that. Right, there's our calculator number. Okay. And so we'll leave that in the calculator, and then we'll just go back over to column 2, and we want to solve for v sub x, don't we? Right? So in this equation, if we solve for v sub x is just going to be horizontal displacement divided by time, which is just 0.527 divided by my unrounded calculator number, right? And that gives us back the answer, what? Let's see what we get. So 0.527 divided by that, 1.19. So that's our horizontal velocity. The marble's rolling at 1.19 meters per second. Let's check it out. There it is. How about that? Okay? You good?